good time to go? All right, so I'm Kye Taylor. I'm a new lecturer in the department. I'm here for only a year, so this is a kind of a quick intro, and then you guys may not see me next year. I graduated with my PhD from the University of Colorado in 2011. Then I went and worked at MathWorks. They make MATLAB and Simulink. And ironic enough, I didn't have enough math working at MathWorks, so quick hit the ejection button and here I am. Really enjoy math, and so far it's been great. So what I wanted to do today was describe search engines, in particular the Google PageRank algorithm. Has anybody heard of PageRank algorithm? Let me just get it. Okay, very good. So does everybody know how it works? Okay, because obviously. So I'll talk a little bit about how it works, what it does. And in doing so, hopefully I'll introduce you guys to a little bit about my research, what I'm interested in. It just happens to be applied in the realm of search engines, but there's a lot of different uses for it in general. So I was trying to remember the other day, can I recall in my memory what it was like to search the web before Google? Like you guys, does anybody remember that? Yeah, Yahoo is one of them. So describe, like, this is the weirdest thing, like, do you remember kind of the change, like when Google finally went online in 1998? Or it wasn't Google at the time. But there was a big change when information retrieval on the web went from sort of static text-based retrieval to incorporating link analysis. And link analysis is just a structure that's part of the World Wide Web, where you've got different pages linking to different pages. So prior to link analysis, there were sort of three main ways search was performed. So you've got some big database. Maybe it's the World Wide Web, maybe it's a library. And you can search this database in one of three ways, or a combination of the three. One is Boolean search. So you've got a bunch of keywords, or maybe query or numbers, identification numbers, and you're just doing simple matches. So you look for, does it have the word car and maintenance, or maybe car or auto? So you got ands and ors, a lot of Boolean operations there. And you can think about incorporating a lot of Boolean searches, and maybe conglomerating the results from a lot of different Boolean searches to come up with another way of querying a database. So my database has a lot of articles in it. I say, here's a query, find me an article in the database that contains stuff on cars and maintenance. So it searches for cars and maintenance. It returns all the pages with cars, all the pages with maintenance. But you may then want to incorporate something like how many times is cars mentioned, so frequency, or maybe location of that word in the document. So when you start to augment data with ways of returning results from a query, you can think of a vector space model. So a page or an article in your database just becomes a point in some high-dimensional vector space, and you return matches that are close enough. And this is a really still used widely today approach, using vector space models. The issue is that when you've got a lot of articles in your database, you have to do a lot of pairwise distance calculations. And that's prohibited for a very large number of articles in your database. And then a third approach is doing probabilistic models. Some sort of like expectation maximization. This article from my database is 90% likely to be the one the user's queried for. Those are very nice and a lot of nice machinery around the expectation maximization algorithm, but they're very difficult to program and implement at large scales. So those are the sort of three typical ways to do information retrieval prior to link analysis. And link analysis is something that is afforded only by the type of structure in the World Wide Web. So if we have just like a library full of books, they're organized and categorized by specialists like librarians or journal editors. And it's those specialists, those experts, who know sort of how things are organized. The World Wide Web, on the other hand, is self-organized. There's no central repository, nobody's in control of it. The organization really just comes from a page linking to another page. So let's kind of talk, I want to draw a picture kind of the scenario, and one of the things at play is the World Wide Web. So it's just a set of all these web pages. And so first of all, it's huge. It was estimated, so it's hard to estimate how many pages are actually in the World Wide Web. In 2004, it was estimated there was about 10 billion pages. And that's in something known as the surface web. Surface web is what Google accesses. There's other parts of the web known as the deep web. This makes up about 500,000 of the publicly accessible databases out there. A company called Bright Planet actually coined this term, and they're another search engine that indexes the deep web. So the surface web alone is huge. Like I said, there's about 10 billion pages. Population of the Earth is about 7 billion, so that's almost 2 pages per person. Each page is on average about 500 kilobytes. So huge, I can't really say that enough. Another interesting challenge with the World Wide Web is that it's dynamic. Meaning, kind of think about the library situation. You know, once a book is published, it's put in, it's printed and it's put on the shelf. Maybe another edition comes out, but that original edition's not changed. In contrast, pages on the World Wide Web change all the time. One study in 2000 showed that 40% of all web pages change within a week. Which is an interesting problem in itself. There's actually a group out there, the Web Archive Organization. You guys heard of this? Anybody heard of the Wayback Machine? Okay, this is another monumental task. It's pretty cool. Go to web.archive.org, and there's a Wayback, and you can basically type in a web page, and it will show you all the different times that page was updated, insofar as that the archive knows about, and how often it's changes. It's pretty cool. It may be archive.web.org. I can't remember.
No, that's right.
That's right? Okay. So that's pretty cool. Changes quite a bit, the web does, which makes indexing it very hard. And then another one of these issues is that there's very little or no regulation. So, you know, when I build a web page, there's nothing that says I need to have ending brackets all the time. You guys have heard of HTML. There's very little rules there. The Worldwide Consortium is pressing for more regulation in terms of consistency between different web pages, so it would be easier to index. But others argue that's part of the web's power, that it's just, you know, there aren't such things, and people can be creative in the ways they want. So these sort of things make indexing the World Wide Web an issue. And so what do I mean by index? So in the World Wide Web, there's all these different pages. And we want to basically be able to get so there's some user. Let me draw a picture of the user. That's right. That's right. Here's my user. And he's making queries. So he's making some queries to my search engine. So we'll just call it search engine for now. And I'll expand on that a little bit. But the idea is I want to take queries from the user and give him back results that are pages relevant to his query. So what a search engine does, so a search engine kind of operates independent of a user, but it really relies on the user. So think about kind of a wall where on this side it's user independent, and on this side it depends on the user, right? A query depends on a user. But what the search engine does, you know, every day at Google, they have sort of a bunch of little functions or modules that work together. One of them is called a crawler. So a crawler is just some module or a function that has a lot of little things called spiders that basically crawl the web. You guys like my spider drawing? Or insects? There's not any things. So the idea is these crawlers, they send out little algorithms to browse the internet and bring back URLs, or pages that haven't been seen before. And these pages are stored in a database, page repo. So a repository of all pages. So the web crawlers go on the internet, they get pages, they bring them, they store them in the page repo. Now, the page repo is sort of just the source code from a page. And, like I said, 500 kilobytes. They can be very large. In general, what Google wants to do, because, there's 10 billion pages, you don't want all that data, you want to compress this information. So there's another routine called the indexer that takes pages from the page repo and basically compresses them. Extracts vital information like keywords, titles, captions, not images, not necessarily images. Though there may be special types of indexers, but I'm just sort of kind of considering a very simple case. So the indexer is able to extract information from original pages and compress it. And then it stores this compressed information in an index. And the index is another big repository. So I'm sort of identifying databases and functions. Databases will have these little corners on them. So I have my index. Here's another database. And the indexer, once stripping pages, stores those compressed versions in the index. So the index kind of has two different parts of it. There's the structure. There's actually, first mention the content index. And then there's the structure index. So the content index is just basically the content from a page. So imagine I got a bunch of pages. What I'm going to do is create an index, and just like the back of a book, when you hear index, you think, okay, I'm going to go to the back of the book and look up a word. And I'm going to find the pages where that word lives. That's the same concept here. Content index is just a bunch of keywords. So maybe the first term is something like aardvark. There's some other terms. Term 10 here I get Aztec. Term 11, baby. And then I get, finally, the last term. Call it M. Anybody know that one? Look it up. And I label next to these terms basically pages that they show up on. So maybe aardvark shows up on page 3, page 5, page 99, etc. And I get basically this index here. Whatever. I mean, these. So there's. Sorry, was there a comment?
Page 3.
The page tree.
Page 3.
Page 3 has got a lot of stuff going on. Page 3 is it's just hitting every mark for me. So I also, there's not, these numbers aren't that high. So let me add one that makes it look a little more like there's a lot of possible pages. Okay, there's a bunch of pages that I could possibly have these terms show up in. So this is what's known as an inverted file system. This happens a lot when you're building databases, and I'm sure some of you guys will be part of that. And so the benefit is, the real quick lookup. I just give you a keyword, you do a Boolean search, return a page. You can also add, augment this information, not only the page number, but you can add things like, how many times does it show up? Does it show up in the title? Is it bold? That type of information. Whatever you do, it all goes into this content index. Okay. And the content index, okay, so the query is actually made to something known as the query module. So he takes queries from the user and consults the content index as well as the page repo, because not all pages are compressed. Some pages are so important they just stay there. They're not stripped of their information. What I'm saying is the query module takes a query from the user, looks at all the pages it has, and returns basically what's known as a content score. It could be a list of, say, 1,000, tens of thousands, hundreds of thousands of pages that are relevant in terms of content. And that's what the web was like before 1998. You just get a bunch of different websites back, or a bunch of different results back based on content, and it was your job to find what was really relevant to you. So then 1998 comes along and two neat things happen. Basically the idea of using link analysis. And this is where, in addition to a content score, so query module will build a content score, we are also going to augment our returns with something known as the popularity score. So it looks like I'm doing minus, plus, minus, so let me do, I kind of want to specify content score here. Now the query module returns the content score, and then this new thing, the ranking module, will return the popularity score. And what is the popularity score? I'll talk about that next. So, the ranking module, he has an interesting job. He's given like hundreds of thousands of documents from the query module that match content relevant to the user's query. The ranking module has to take all of that information and the structure index and build basically a result to return to the user. Result. So the idea is, what is this popularity score? How does this ranking module work? One thing I also want to point out is this crawler, he might also use this structure index, because the crawler needs to find parts of the web page that haven't been crawled yet. So in that structure, the structure is basically links between web pages. The crawler is careful to follow links, basically, to crawl from one page to another. Are there any questions about kind of the setup here? Okay, so I want to talk about this ranking module and how it develops a popularity score. Is it okay if I do it over here, kind of leave this picture? Okay. So it's interesting. 1998 was one of those times where people were all working on the same thing. They wanted to index the web. They wanted to make searching easier. And it happened in 1998. Two papers were published. One was on hypertext-induced topic search by John Clydeberg out of IBM. The other was PageRank by the two Stanford students, the PhD candidates in computer science. They both sort of relied on theses. So the PageRank thesis was one that important pages, so PageRank, actually I'm just going to probably focus on PageRank because we don't have a lot of time. But the HITS algorithm, the hypertext-induced topic search, is basically, it's very similar. It's crazy how similar these things are, but it was developed separately and at the same time, so it's one of those weird things, right? But anyway, PageRank, it has the big idea is that a link can be thought of as a recommendation. So if a lot of pages are linked to by other pages, that's to say he's highly recommended. Okay, so this is its main idea, but it tempers this with the fact that, so here's an example. Think about getting a recommendation from Donald Trump. Let's say I rolled in here and I'm like, I got a recommendation from Donald Trump. I roll into a business, not here. It's not going to work here. So I roll into a business on Wall Street. I'm like, Donald Trump's going to recommend me for this job. What about it? Are they going to hire me or not? Why not? And don't. Okay, very good. Yes, I kind of walked into that one. Why? Let's say there's no prejudice against Donald Trump. Let's say, what might hurt his recommendation? If he gave out like 400,000 of them, right? Maybe if you all had recommendations. So the idea is that the rank of page I, so let's actually say RJ, so this will be the rank of page J, is basically a sum over nodes that link to J. So I arrow J. Oh wait, actually I need to draw a picture here first. I see. Let me I gotta get rid of the user.
I'm sure you have computer engineers everywhere.
Yeah, I know. So the idea is we can think of these web pages as vertices of a graph. So each vertex here is a web page. I got 4 web pages in my collection. I can draw arrows between vertices to represent links. So in this example, 1 is linking to 2, 3 is linking to 2, 3 is also linking to 1. And so I can keep doing this. Now here 1 links to 3, so that kind of links back and forth. And then maybe I got something like this. So the idea is that I can compute the rank of page j by looking at sort of the structure in this graph. I can sum, like if I'm trying to compute the rank of vertex j or page j, I can sum over those vertices that link to j and look at Ri divided by the out degree of I. So this degree super plus of I is the number of links from page I. So it's this idea that so let's say Rj is high, then these Rj's, then these terms will be relatively high. So the thesis, the thesis is that an important page, or a page that's deemed popular, high popularity score, will be pointed to by other popular pages. And so it's somewhat a circular hypothesis, but it leads to really nice mathematical equations. Are there any questions about this?
With that definition, doesn't the rank of 1 and the rank of 3 are defined in terms of each other?
Yeah, so actually, exactly. So the rank of 1 will depend on 4 and 3. Does that make sense? So yeah, and the rank of 3 depends, it's like I said, on 1, and that's it actually in this particular example. Are there any other questions? Okay, so now this equation is for all j, right? And so you can actually write this in matrix vector form as basically pi transpose equals pi transpose h, where pi j is rj. So the jth entry of this vector pi is rj. I call it pi because I'm thinking other you guys might recognize this. This is a left singular or left eigenvector of this matrix. Has anybody seen left eigenvectors called pi before? Oh, okay. Never mind then. So this is actually an equation. So here's the deal. Let's think about what h looks like for this example. So h, can everybody see this? I'm sorry. Okay. So h, in the first row, I think about where I can go from node 1. So I can go to node 2, and I can go to node 3. So what I'm going to have here is, and I have 2 outlinks. So what I'm going to do, you guys will see how this all works. So I get 1/2, and then it's 1 to 2, and then 1 to 3. So like 1/2. And then now I go, so the idea is hij is equal to 1 over the degree plus of I. So the out degree of I. So the out degree of 1 is 2. The out degree of 2 is 0. So actually I just get a bunch of zeros in that row. Now 3 connects to 1, 2, and 4, has out degree of 3. So I get that matrix. And now 4 just connects to 1, has out degree 1. So I have that. Okay, now look at this and look at this. Does this look familiar to anybody? Thinking like Markov chains? Okay, Markov chains. Who's heard of Markov chains? These are great, right? So this looks like a transition probability matrix, almost, except for that, right? So this thing is a substochastic matrix. The idea is, so here's where everything gets cool. We represented the structure of our little web, of our World Wide Web. So our World Wide Web just had 4 pages. We represented its structure using a graph. Vertices were pages, edges were links between pages. Imagine now we've got some surfer on on the web, a web surfer, who is just surfing from one page to another. So, and he's a random surfer. He doesn't know what he's just surfing the web, dude. So at one, he's like, okay, I can go to node or page 2 or page 3. Let me just choose one of those at random. So the idea is we want to evolve that process, kind of create a Markov chain where there's a random surfer who's bouncing around between web pages. And basically, we'll figure out how long he spends on average at each page. And the more time he spends at a page, the more popular it is. Does that make sense? So that's our goal. We got a random surfer. We want to let him do his thing. Ultimately, come up with how long he spends at each page. That will give us our popularity score. Now, the fraction of time he spends at each page is given by entries of pi transpose. That's sort of a Markov. I'm just saying, oh, I know Markov chain, so boom, that's what's up. So the idea is, can I solve this equation? If so, can I solve it uniquely? The idea is, Google wants there to be a unique ranking. So what we need to do is modify this equation so that we can solve for a unique left eigenvector with eigenvalue 1. Okay? So I have until 1, right?
You can go over.
Oh, okay. I won't go much longer. I was really aiming for 1. So let's do this. So let's talk about the ways to make that solution pi transpose or pi actually unique. So those of you who've taken Markov theory, what is required for a unique stationary distribution? So this pi, here's my stationary distribution, right? Does anybody remember what I need, or what is sufficient for and actually necessary for a stationary distribution? Shout it out. So I think you guys will remember. Let me talk about some issues, right? So think about node 2. So that one you pointed out was an issue. What's the problem with node 2? Let's say my random surfer surfs to node 2.
So he eventually will have to surf to node 2 and then stay there forever.
So yeah, random surfer, he gets node 2, he's stuck. So one of the things for a unique stationary distribution was irreducibility of the Markov chain. You guys remember that word? Irreducibility, or strongly connectedness. It was basically the property that I need to be able, from every node in my graph, I need to be able to make it to another node with a finite set of traversals of edges. So I can't go from 2 to 1. So one of these things, known as the stochasticity adjustment, is I'm going to actually look at a matrix S that is H plus a rank 1 update. And that rank 1 update can be written as 1 over n A E transpose, where E is a vector of all ones. So it's my column vector of all ones. And A, I is 1 if page I, or node I, has no outlinks. And 0 otherwise. So what this does, it basically will change that matrix and basically say, when I hit one of these pages with no outlinks, I can go to any other one with equal probability. So that is the stochasticity adjustment. So now this matrix is rho-stochastic. And not necessarily irreducible yet. So to make sure we have irreducibility, we need to do one other thing. So irreducibility was one of the things for a stationary distribution, but there was something else I'm also looking for. And that, if we can think about it, what highlights it is if we look at a simple graph like this. Think about this graph. If I'm a random surfer. So my H looks something like 0, 1, 1, 0. If I start at node 1, so like this is my initial configuration, that just turns into 0, 1, right? And then if I go 0, 1 times 1, 0, I evolve the process from that kind of distribution I go back to 1, 0. So this is a cycle, and I want to avoid cycles. I want to avoid periodicity in the chain. You guys remember that term, aperiodic? I want an aperiodic Markov chain. So to fix aperiodicity and imply, and also ensure irreducibility, I make another adjustment known as the primitivity adjustment. So I create a matrix G that is a convex combination of S and a matrix known as the teletransportation matrix. So alpha is in between 0 and 1, and E is this teleportation matrix. It's just such neat things, right? If you're going to talk about your work, call it cool stuff. So this teleportation matrix is simply, it's kind of just like this rank 1 update, but instead of A, I'm going to do just E. That is to say, so here's the idea. Think about that random surfer. Or think about yourself when you're on the web page, or surfing the web. You navigate from page to page, you follow links. At some point you're like, I'm at a page where I'm not going to follow links any further. What are you going to do? You're going to go to some other page, you're going to teleport there by entering that page web address, right? So that's what this matrix E is supposed to represent. That with some proportion of time, 1 minus alpha, I randomly teleport to another page. And so this matrix G is the one we end up studying. So this is called what they call the Google matrix. It's irreducible, aperiodic. This implies primitive. Now primitive, a matrix is primitive if its largest eigenvalue is unique. And, well, it's all positive. It's for some power. Every entry is positive. But in our case, it's to say that our matrix G will have one unique eigenvalue, the largest one. Or sorry, the largest eigenvalue will be unique. And that's very nice, because what we can do is use fast algorithms to solve for the eigenvector. We just need one eigenvector. It's associated with the largest eigenvalue. Does anybody have an idea what method I'm going to use to solve for that eigenvector? Those of you who have maybe taken numerical linear algebra or something like that. Power iteration? Power method? Okay, maybe that's okay. That's okay. The power method is a really sweet iterative routine for computing the dominant eigenvector, or the eigenvector associated with the dominant eigenvalue of the matrix. So, to compute, we use the power method. And we can essentially write it as, let's say, pi k transpose, so that let me actually say that k plus 1. So I'll generate a sequence of these vectors pi. By essentially just hitting them over and over again with the G matrix, right? Because think about, so pi 1 looks like pi naught G. Pi 2 looks like pi 1 G, or pi naught, transpose, G squared. So I start looking, you just keep on going. You look at powers of this matrix when it's hit with another vector. And this thing will converge in special cases when you have a primitive eigenvalue. It will converge to that dominant eigenvector. So Google uses the power method to compute the stationary distribution pi. Okay. Now, I'm kind of hoping somebody might ask me some questions here, because think about what I did with these adjustments. So H, think about the structure of H. Think about how many zeros there are in H. So in my little example with 4 web pages, I drew a lot of links. But in general, 10 billion web pages, one web page links to how many other pages out of that 10 billion? Like 10 or 20 maybe max, right? So H is a very, very sparse matrix. Very, very sparse, very few non-zero entries. And so matrix multiplication with H is okay. But what about G? G is fully dense. And so the question is, how does this work? How can the power iteration work and be useful to Google when G is completely dense? And it actually is very, so do you guys understand that issue? I want to do a lot of matrix multiplications, but I have a very dense matrix, so that kind of says, wait, don't do that. But your saving grace is the fact that G is just a bunch of rank 1 updates. Who loves rank 1 updates? Makes everything easy to compute. Sherman-Morrison formula, we talked about it, right? Rank 1 updates, you can invert a matrix. So we actually can take advantage of rank 1 updates here. If you think about G, so that's, we get, basically, we can expand this. So you're going to get alpha times S, which is H plus 1 over N, A E transpose, plus this 1 minus alpha, 1 over N, E E transpose. You guys okay with that substitution? And then you guys see what happens? I can pull that E transpose out on the right. So basically, I can rewrite all this. Let me factor that pi k through and pull out this E transpose. So I get pi k transpose H alpha. So now here, this matrix vector multiplied, that is sparse. Then I'm going to have plus alpha over N, A over N, E transpose. And so I get the pi, oh, this is what's cool. So check it out, I'm going to put the pi k there. And then I have plus this 1 minus alpha over N. Then I have a pi k times this vector of all ones. So pi k transpose times E. Pi is a distribution. So if I sum all of its components, I just get 1. So I have basically the scalar E transpose. And so I have this very sparse matrix multiplication, and then just components of those update vectors A and E. Okay? So I think that's where I want to leave it. The notion of studying graphs and sort of random walks on graphs is really exciting to me, so if you guys want to talk more about it, definitely excited to do that. Please don't hesitate stopping by, and I have another talk November 1st, that colloquium, where I build on just some graph ideas if you want to check that out. So, any questions? Okay, thank you guys.